Okay, for this problem, I've already actually set up a lot. This is a block is given an initial speed of 4 meters per second up a ramp, inclined at 30 degrees above the horizontal. The coefficient of friction is 0.2. How far up the ramp will the block travel? So what makes this problem a little bit interesting is that we're given indications that this is a kinematics problem. For instance, initial speed of 4 meters per second. And what we're looking for is how far up the ramp. So these are indicators that we have a kinematics problem. But the other thing that we know or should notice is that we also see the coefficient of friction. And that's indicative of a force problem. So what we probably need to do in this case is go ahead, draw our forces in, but also draw in some kinematics indicators as well. So for this problem, I've already drawn the ramp and the block, and I have a force up this way, perpendicular to the surface. That's going to be the normal force. I have a force of gravity down this way, which I split up into the perpendicular and parallel components. And I also have a force of friction directed down the ramp. And this is probably one of the most important things because the block was given an initial push at some point prior to the start of this problem. The block was given an initial push so that when we notice the block, we see it moving up the ramp at 4 meters per second. Friction is going to do everything that it can to oppose that upward motion of the block, and so it's going to provide a downward force. So in this case, we have friction and gravity working together, which should cause the block to slow down and stop pretty quickly. I've also drawn in a initial velocity vector and the initial position and the final position of the block. And then over here I've just drawn more explicitly my force diagram with my x-axis and my y-axis. And I'm going to go ahead and make this the positive direction, and I'll go ahead and make this the positive direction as well. And I can see that I've used the same angle here as the angle of incline. That's because I rotated the x and y axes by 30 degrees. And now I'm going to list some givens. So for my givens, I'm going to do some kinematics givens, and I'm also going to do some force givens. So for my givens, it's probably the worst givens that I've ever written. I have x naught, which equals 0. I can just set that equal to 0. My final position, I'm not sure. That's what I'm looking for. The initial position I know as 4 meters per second. Final position, it's saying where will it be when it stops, so I know that that's going to be 0. The acceleration, no idea. And the time, no idea. So those are my two things. I don't know how long it's going to be accelerating, or how long the acceleration will last, or what the acceleration will be. Because I have information on forces, that doesn't help me with time, but it does help me find the acceleration. So if I get the acceleration, I should be able to use the no-t equation to figure out what this velocity is. So that's going to be my angle here. If I can find the acceleration, then I can figure out how high up the ramp this box goes. So before I get that information, I should list some givens as far as forces go. I know that the coefficient of friction is 0.2. I know that my angle is 30 degrees. And if I want to, I can write out, for instance, the force of gravity in the x direction will be, in this case, negative mg sine of the angle. And in the y direction, it will be negative mg cosine of the angle. And the reason why I chose negative for each the x and the y directions is because this was my positive direction up this way. Gravity is pulling in opposition to the positive direction in each case. So now, because I kind of have an idea of what's going to take place here, as far as needing to find the acceleration, ultimately I'm going to need to find out what's going on in the x direction, which means that I'm going to need to figure out what is friction. But to find out what friction is, how large friction is, I'm going to need to get the normal force. So I'm going to start off by doing my first step will be a sum of forces in the y direction. And that's equal to m times a in the y direction, which really ought to be equal to 0. So now all I need to do is add up what forces are acting in the y direction. I have a normal force, and I have a force of gravity in the y. So I do normal force plus force of gravity in the y. Those are the only two forces I have in the y direction. That equals 0. I know what the force of gravity in the y is. So I have normal force minus mg cosine theta equals 0. And so I get that the normal force directly opposes the part of gravity, the component of gravity, that's trying to pull this block through the surface down this way. So there I get my normal force. Next step is going to be to figure out what's going on with the forces in the x direction. And this is where I'm really going to be looking to find out what the acceleration is. I don't know what that is. But I do know the two forces. I have the force of friction, and I have the force of gravity in the x. And these two forces are going to work together to cause a negative acceleration. So I'm going to have negative mu times the normal force minus mg sine theta equals m times a. And now I just take this and plug it in here. So I will have the opposite of mu mg cosine theta minus mg sine theta equals m times a. And that means that I can cancel out the m's. It's in every term, so I can get rid of it. Some people like to think they can get rid of the g's. Not so, because it's not in this term. So I can't get rid of g's just now. The last bit that I need to do then is just solve for a, which I pretty much already have. I'm just going to consolidate a couple of things here. So I have g, let's do the opposite of g, times mu cosine theta plus sine theta equals the acceleration. And if I wanted to, I could figure out what exactly this is. But as of now, I don't think I'm too interested in finding out what that acceleration is. I'll just go ahead and actually I'm going to pause this presentation and probably split this into two parts. Okay, so on further review, I've decided that I'm going to be able to hopefully get this done in one session. So what's going to happen then is I will just go ahead and solve for what's going on kinematics-wise. So I laid out my initial position and the final position and what the velocity is in the y direction. And to do the third step then, what I need to do is v squared equals v naught squared plus 2a delta x. So this one's just going to be 0. The final velocity, that's the whole idea, to figure out where it stops. And so now I just subtract a v naught squared from each side, set it equal to 2a delta x. And I know that this is a. So I'm going to take v naught squared divided by 2a equals x. I could technically put in x minus x naught, but x naught is 0. So I have the opposite of v naught squared divided by 2a equals x. And opposite of v naught squared, I go ahead and I plug in this whole mess over here. So that's actually the opposite of 2g mu cosine theta plus sine theta. And this is actually not writing very well today, so I'm going to try it again down here. So I have x equals the opposite of v naught squared divided by the opposite of 2g times mu cosine of theta plus sine of theta. And I can plug in the numbers, and I should get 1.21 meters as the answer. So there we are. There's our answer. And one of the things you should do is always make sure that your answer makes sense and that the solution right before you plug in numbers makes sense. So here it says that the further we go will depend in part, and I can make these positives, that'll make more sense. So the further we go is determined by how fast we're going. So the faster we go at the start of the problem, the further up the hill we'll go, which makes a lot of sense. This says that the harder gravity is acting, so if we took this to the moon, for instance, where the acceleration due to gravity is less, then it would go further up the ramp. It also says that the larger the coefficient of friction is, so the larger this number down here, the less far we go up the ramp. And then there is a factor between the angles. They're both, in this case, working to bring the block to rest, so it doesn't matter as much how big the angle is. It matters, but since they're both working together, it doesn't matter as much as it would if, say, we were trying to slide the block down the ramp. Alright, that's it.